Okay, so welcome everybody. This is the second and the last part of this 2 days workshop on cloud native. In the previous session, we have seen the basics of containers and some theory about cloud computing and cloud native, and we also saw that how containers are useful in modularizing large scale applications. And we used a tool called Docker to create containers out of raw source codes. And we saw that this whole thing is automated process, and we do it through something called a Docker file, where we list instructions given by directives, and these directives are defined in a special language, which is Docker specific language. And we also mentioned a couple of limitations of having just container system to deal with large scale applications. And the main purpose of today is to fix or address those challenges by using orchestration framework. And we are going to use open source orchestration framework called Kubernetes. It was initially developed by Google for managing their container systems, and then they made it open source. We'll talk about a couple of nomenclature and terminologies that we need to be familiar with to go along with cloud native development. And with these setup, we will then move forward with something called reconciliation. It is a sort of a new kind of a term where we assume that all the configuration of the application needs to be synchronized with the running application, and it is not possible humanly to monitor all these states and keep them on sync. So therefore, there's an automated process which is deployed, and this is called GitOps. Why Git is there in that nomenclature? We'll also discuss that, and then we will see that how applications staying in the containers can be orchestrated in a Kubernetes cluster. We will create a cluster from scratch, and then with this, the whole objective is to um, sort of give you an overview that what is the pipeline of operations that takes place after a developer writes a code, and that code gets to production, and it is maintained in a cloud native way. So with that being said, I'll first start with the repository. So I have made some push yesterday in the repo. So if you open the repo now, let me just refresh it. Yeah. So if you open this repo now, you should see there's just one branch called main branch. And as you can see, a couple of updates were made in the last couple of hours. Some files have not changed since it was created, but the rest of the files are now added. And then in the README, there is a lot of change. I have added a reference architecture. So this is something that we will follow today. We will build this pipeline step by step. And you might be surprised to see there's no container in this picture, because the containers will be inside certain components in this picture that we'll discuss. This is a pipeline that we'll build today. So previously, the tutorial was until this point. So the verification um, of the images, the Docker images. But now we will resume from there. We'll first do something called a push. We'll see what this operation is. You might have seen push for Git repository, but we'll also see how we can make push in a registry or a artifact registry, as you mentioned in the last session. That this is a place where we keep the images. Okay, so from there, we'll move on to three tasks. The first one is the deployment of Kubernetes. We'll start by extending the capability of the existing VM by adding a Kubernetes cluster on top of it. And then the second task is optional. So this is just to show after you install Kubernetes and without having a GitOps pipeline set up, how can you run Kubernetes or applications within Kubernetes manually. And then we'll also realize that this is not a very scalable procedure, because if a application fails, then someone has to come and restart the application. That is not manageable when the application scales beyond certain critical value. So then we move on to task number three, which is Argo CD integration. And here we will understand the concept of reconciliation. We'll go through certain steps. Everything is listed here, so don't need to take any notes, commands, and everything. And then we'll verify that we'll find what is called live system. So a live system would look something like this. This is Argo CD UI. And here, if I open it, you will see a very nice GUI that kind of shows us everything is in sync. And as an operator, that's what you want to see, that everything is healthy and everything is green in your UI. And what it says that a test application is running with a couple of things that we might not understand at the moment, but I'm sure after we finish this session, we will know what is this. I just want to show you something quickly. Um, where we want to get today. Okay. So imagine this is a live application, and there's some other places where it shows even better. For example, this topological view, it shows that this system, whatever it is running and it is live. Okay. Now, if I go back to my previous view, and again, these views we'll discuss in details. It's just for showing you where we are heading towards, so you know what to chase. Um, so if this is a current system, and if I go to my VS Code and I, let's say, make some changes, and again, we will get to know what these changes are. So some new files got added in our VS Code since the last time we saw it. And if we go to conf folder, which wasn't there before, you'll find that some new things are there. SPF client and SPF server.yaml, these files were not there. These will be called Kubernetes manifest files, and these files will um, this file will contain information, what we call infrastructure as a code. Means with this file, whatever info is there, it is sufficient to tell a Kubernetes cluster to spin up various pieces of softwares, make logical connections between them, so they represent themselves as a logical infrastructure. So this infrastructure is explained through a code, so we can automate it. Now here you can see there is one thing called replicas, and replica normally tells us that how many copies of a particular entity we need in our system. So just by seeing the names, you could guess that this is a client, and this represents the SPF client that we already saw in the last class. So what if we want not just one, but 5 copies of this client? A real life use case would be every single user, when they connect, they should get their own copy of the client, so they don't interfere with other existing users. So when the user base increases behind the scene, somehow you can correlate with the fact that the replicas increases. So let's see, if I make it 5 replicas and I quickly go through the process, what will happen from this change of my intent that I want to scale my application to 5 times to the point that the application actually gets scaled to 5 times. Let me show you the process. And throughout these sessions, we will see how we eventually get there. Okay, so I have a extra script that I did not discuss in the last class, but it's there. It's called the push.sh. I will not show the content at the moment. We'll get to that. So as a, let's say, full stack engineer, you would be having a system like this. So let's say you get a request to scale up your client side to 5 times. You go to your client configuration file, you make change to 5, and now you run this script, push.sh, and this script takes 2 inputs. One is the branch name at which this push is going to be made, and a commit message. I'm assuming you already know what these 2 things are. So I want to first of all push into a GitHub branch. branching out from my main branch, and then I will accept that change and merge that branch afterwards to the main branch. And this change needs to be kind of logged somehow. So I'm going to put a message. So I'm going to say push .sh. So I'm going to make the push event, and I want to put my current branch. The current branch you can get by saying git status, and git status will show that my current branch is K8s and K8s add-on. K8s is a shortcut of saying Kubernetes. So I'm just copying this, and what I'm saying is git status. I put this branch name and I put a message. Let's say um, scales up client, because I'm scaling up the replica of the client, and I press enter. Something is not working. Okay. So what I was going to show you is if I make these changes here, so I make a change in my GitHub repo and I change replica, for example, it should directly go and scale this without me doing this manually. Okay. So that's the task for today. And where I want to go from where we ended up in the last class is having containers only sitting in my local registry. Now I'm going to take it to a remote registry, which is Docker Hub, and then you're going to pull it from there. Okay, good. So start with, let's say, our presentation. So I'm not repeating what we did already in the previous class. We understood what are the basics of cloud computing, what is cloud computing, and what are the advantages of cloud computing. We also saw the different, types of services which are hosted in cloud in terms of public, private, or virtual private. We then move on to let's say hybrid cloud, which is a middle ground between private and public cloud. And this is basically separation of concern. So part of the application which requires more security that stays in your campus, the rest goes to the public cloud, and you should have a seamless connection between them. And we also kind of saw a similar example with our client server application. So if we can break down applications in a way that they could communicate with themselves, these communication will take place over API calls. And the type of APIs that you're going to use in this lab, and mostly which is used over a cloud native, is called a RESTful API. So RESTful stands for representation of state transfer. It's a design pattern through which applications communicate. The main idea of RESTful is it is a request response protocol, so it is implemented over HTTP, and it's a stateless protocol. So any request, when it appears to the server, it is treated in isolation compared to any other request. Okay, so no request would be influencing other requests in RESTful communication. Every request is a request by itself. Okay, so we also saw IaaS, PS, and SaaS, the three types of the three layers of cloud services, and what are the benefits. Then we saw the technologies that make cloud computing possible, namely the SDN and NFV technology. And we also saw in the NFV architecture, there's something called the MANO, Standard Management and Orchestration, which is standardized by ETSI. And now if we move on, um, we saw the different component that makes up cloud native technology. So cloud native is the design pattern through which you write applications that go and run in a cloud. Okay, so microservices and containers that we have seen already. Scalability, I wanted to show a demo. It didn't work for some reason. So we'll see what's the issue. And the way we bridge the gap between containers without scalability and containers with native scalability is through a process called orchestration. So what orchestration provides is a way to manage containers at scale. And then we'll also understand something called CI/CD. continuous integration and continuous delivery. This is the process in which, for example, you as an application developer, if you have an app and you might have seen these incremental updates in the application that you use in your phone, that the developer might have found an issue in the app or added a new feature in the app. You don't need to go and manually look for if there's an update or not. Somehow automatically these updates are made. Your application suddenly gets updated. Okay, so how this is done, how the developer, when they push their update in the repository, triggers the target side where the application is in service. Okay, and how smoothly this application is replaced. So even if you are using the application while this update was made, it will not hamper your quality of experience. So we will see how exactly this is done, and this is where the CI/CD pipeline will come into play, and we'll see Argo CD in this example, which would help us doing that. Okay, we also saw microservice architecture as one of the key feature. It's a concept through which you break down application into smaller pieces so that highly cohesive part of the application stays together and they become loosely coupled with other highly cohesive part of the applications. So if one part of the application fails, it doesn't affect the other part of the application. And we saw that containers are the actual technologies through which we achieve this. We saw the container life cycle through Docker. We went through this full life cycle in the last class. And what we did last time was we simply cloned the repository, where is not supposed to be the case in a real world, and that is what we'll see today. The repository should be hidden from the target environment. But just for the sake of demonstration, we did it last time that we downloaded the code from the repository and we did some building process that builds the images and it stays locally. And then we ran the images to test that if the images are working okay or not. And they were working okay. We could do port forwarding, could access the applications from a remote host. So things were all going right. Now we are moving towards today's topic, which is orchestration and management. So I just want to take some time on explaining the reason why this technique exists. Otherwise, you won't be able to appreciate what are we doing with Kubernetes and clusters. You see, when long time back when containers started, slowly getting into the development process, software design work, migrating from the old school monolithic design to microservice design, and containers were used for creating the microservices. Very soon, people realize there's a problem that containers are good for isolating source codes from the other executing environments. However, when they start scaling, they become a bottleneck. So container management tools like Docker, they came up with solutions like Docker Swarm, then Docker Stack, Docker Services. There are some techniques that Docker also came up with, which had the intention of solving this problem, but they didn't quite manage to solve it the scale at which industry would have wanted. So at the same time, Google, they're also migrating their processes into microservices, and in the data centers, Google internally developed a tool that would manage containerized environment. That tool was Kubernetes, and eventually Google open sourced it through Linux Foundation, and a new kind of standardization was formed called CNCF. CNCF stands for Cloud Native, um, can't recall, yeah, some foundation, Cloud Native Computing Foundation or something like that. So CNCF is a responsible body or the standardizing organization, which is responsible for sort of laying the foundations and setting the rules for cloud native development. So if you want to develop things in cloud native way, how would you do that? This is what the job of CNCF. So in an orchestration environment, what happens when the container starts scaling? We need to somehow add certain extra features. First is storage orchestration. So, as I mentioned last class, that the containerization is basically adding an extra layer of protection using some features from Linux called Linux Jail, or Chroot Jail, through which you can give constraints to a executing application, that what they can see or what they can't see. And these abstractions are called namespaces. And these namespaces could be of different types. You could abstract application in terms of process. You can abstract application in terms of networks, storage. So you can specifically say what proportion or what part of the physical resources, CPU, memory, storage, network, a particular application should get. So the underlying principle stays the same. You are relying on the Linux kernel to get this access. But for example, if you're designing a very complex system where you want a particular storage to be shared by multiple containers, or let's say one container may hand over storage right to other containers, these sort of challenges were the ones that made people realize that, okay, we need something more than just Docker. Similarly, service discovery and load balancing. So think of, if you're scaling the application, and instead of one, you are, let's say, running 5 containers with the same application. So the idea is, when instead of serving one customer, when there are 5 customers, then we could redirect these 5 customer requests to 5 different containers, and they will run in their own execution environment. But in that case, we need some kind of load balancing, that who would distribute this load. There is no native control in Docker that does this. Auto scaling, I wanted to show you in the demo. It didn't work, but that is what I was trying to show you. We'll see what's the issue is and how to fix it in a moment. And then automated rollout and rollback. So if, for example, an application fails, or what I just explained or give an example of, that if you suddenly get an update, then how would you apply that update without stopping the application? That is what automated rollout and rollback is, and we'll see that. And self-healing is something that is implicit. So if somehow the application fails for some reason, it needs to respawn itself. So all this, management and orchestration job, it was not, part of the capabilities that initially Docker brought up. So very soon, engineers realized that we need an extra layer of, management on top of the the container. So if you see this diagram on the bottom, what you can what you can figure out from here is, okay, we have Linux at the very base. On top of the bare metal hardware, on top of this, we have this chroot, cgroup, and namespaces features from the kernel. And then we have container runtime, which allows containers to run. And then on top of, we had containers before. Now, when we are moving forward, from the Kubernetes perspective, Kubernetes says the unit of execution might not be just container, it could be a set of containers. There is a limitation how many containers you can fit in that set. I think it's 8 or 9. It depends, but it's not indefinite. So there are limited amount of containers which you can club together to create what is called a pod. So the idea is, as I mentioned before, highly cohesive and loosely coupled applications. So highly cohesive applications, or highly cohesive containers, which would require very frequent interaction between them. So as if you are moving one of them is moving all of them, should stay together. And that is the idea of a pod. So a pod is a collection of containers. So in this diagram, what you can see, that we have got 2 pods. The first pod has 2 containers in it. Each container has its own app, libraries, and packages. The second pod just has 1 container. So a pod must have at least 1 container, and the number of containers should be less than a certain number. And this is the minimum execution environment that Kubernetes is for execution. So all these additional features I mentioned, storage, auto scaling, rollout, all these features gets ingrained in this Mano platform that manages pods, not containers. And inside the pods, we have containers. So these pods will go into what is called a Kubernetes hierarchical architecture. So Kubernetes has a two-layer hierarchical architecture. Um, we have one component called a control plane. This is the brain of Kubernetes. This is where all the management processes run. And you can see some components here: API server, scheduler, etcd. These are all the brain components. So this is where the actual algorithms for management of the containers run, and they communicate with a set of worker nodes, and the worker nodes are the workhorse. So this is exactly the place where the CPU and memory would be used for running the containers, and the components are far less compared to the control plane. And this is exactly where the pods run. And beneath the pod, we have container runtime. So very quickly going through the most essential component. This list of components are non-exhaustive. So there are other components in Kubernetes which are not described here, but these are the bare minimum that you must know about Kubernetes architecture. So Kubernetes works in a hub and spoke model. The hub being the control plane, which should have visibility of all the spokes, and the spokes are the worker nodes where the actual execution takes place. Kubernetes is also designed in a client server manner. So the control plane runs the API server, and this is the component through which all other communication takes place. So, for example, security, I haven't put in this, but if you want to add security, who can control what or which worker can request what, those sort of things are managed by API server. So if you have to add some filtration of requests, you should be applying them at this stage. Okay, now with this API server, there are three other components. The first is a scheduler, and the scheduler is responsible for allocating workloads to the work nodes. So, if, for example, a request for deploying a new pod comes in, then the job of the scheduler is to find a worker node which has enough capability and available resources to run that particular pod, and will schedule that pod in that particular worker node. So that's the job of the scheduler, uh, mainly distributing tasks into the worker nodes. Um, Controller manager, this is another entity, and this is not just one entity, but it is an entity that manages a list of entities called operators. Operators are, you can think of their plugins, their additional features that you can add on Kubernetes control plane. We'll see one of the operator today is called Argo City, that will add additionally on top of an existing Kubernetes control plane. Okay, so some operators are in build, like replication operator is in build, and but there are other operators that you can add. So with this process, you can increase the capability of Kubernetes based on your requirement. If you're familiar with any other tools that allows plugins, you know what I'm saying. So the tool comes with a vanilla flavor, and then you can add additional capabilities based on your requirements, and they come in some sort of format, that format in case of Kubernetes SQL operators. Now, to do all this management, it needs to maintain some kind of a database, and that database is called etcd. It's an open source key value store database, so it doesn't store data in a RDBMS format like tables. It stores data in more of a key value pair combinations. So this is what the internal components of a control plane of a Kubernetes is. As I mentioned, this list is not exhaustive, so there are other components which is not required for our discussion today. Then this API server also communicate with Kubelet, which is the listening entity of the worker nodes. So the kubelet is responsible for taking instruction from a controller and instructing the controller container runtime that, okay, spin up this many um, containers behind the scene. So this interaction from the Mano to the container runtime, this bridging is done by kubelet. And kubeproxy is an entity that runs with every worker node, and the job of the kubeproxy is to collect the awareness of that particular um, worker node. So, for example, various utilization metrics. If a container is failing, there are logs. So, all these informations are collected from the container runtime and some other Kubernetes features. So, kubeproxy's job is to collect this information, and those information gets breached with the API server through kubelet. So that I'm moving on to the next slide. Um, a most important thing to understand is the different types of encapsulations that Kubernetes offers. So at the very basic, we have an application repository where the application code resides, which is GitHub in our case, and container registry, which is Docker Hub, where the Docker images are kept. So when we pull images from Docker Hub, um, we get the artifacts, and then these artifacts are run. So we get containers, and we can run such n number of containers, C1 to Cn. The first encapsulation that we put on top of it is called a pod. So as I just mentioned, that pod is a set of containers which are highly cohesive in nature. And because we are clubbing them, there's some new information we need to add. For example, you can give a name to this group, and this information needs to be stored somewhere. And this is called a metadata. So this is where we keep the information about the pod, and the pod is a collection of containers. So it should have some kind of reference to the the Docker registry or the Docker image from which this pod will be built. We'll see exactly how this information looks like in a moment. Um, Now the problem with pod is, okay, this is the lowest possible execution environment we can get into, or the unit of execution for Kubernetes. But some feature it doesn't support. One of the feature is replication. So replication means, as I just said, if I deploy one pod and I want to scale this pod, let's say n times. Now try to understand what I'm saying here. A single pod is a collection of a finite amount of containers. So just imagine a pod contains three containers. Okay, so C1, C2, C3 goes inside a pod. So n is three. That is a unit of execution. So if I am saying that we are scaling the pod three times or four times, means how many containers I'm going to create eventually. Three containers for one pod and four search pods. So 12 containers you're going to create. So this sort of a replication is not natively possible with a pod. And this is actually maintained by one of the controller manager called the replication controller manager, which makes this happen. So the replication controller manager will go and speak to the respective kubelet to spin up new containers in the respective worker node. So that extra feature is only available if we encapsulate a pod into something called a replica set. Okay. Now, replica set is pod with replication capability, but it doesn't have something called a rollout capability. So the thing that I just mentioned, that we have, let's say, an application which is being served, and somehow the application gets updated. So what happens afterwards? We need to somehow stop the running application and run the new application. And if you abruptly just stop the application and then you start running, there are two things that may go wrong. Number one is, what if the application you're trying to run now, replacing the old application, if that is buggy? So that application will not eventually run, and the client who were connected with the application that just terminated would be signed out, okay, or face any issues or jitter in the consumption side. So therefore, it is a good practice. So that the first issue was this. The second issue was, um, so when you roll out applications. Maybe the application was not buggy, but also it required some kind of downtime to stop the existing application and restart the newer version. So that is also a glitch from the user side. Maybe you are watching a video and suddenly YouTube gets restarted. You may lose some of the information that you are consuming. So that is not acceptable from customer side. So it's a better approach is to keep that existing container or existing application running while respawning or spawning a new um, um, application with the latest code. As long as this code becomes live and you see there is no error and this code is now ready to take over, then you stop the old application and then you move to the new application. So these are the different rollout strategies you may have a look on after the session that Kubernetes offers. So this additional feature of rollout is not present in case of replication controller. Or replica set. So that extra feature of rollout with replica set is called a deployment. Now, deployment um, can only communicate with other deployments inside a Kubernetes cluster. Okay, they don't have access to the networking resources directly. For that, we add an extra layer, an additional entity basically called service, and we say this service is linked with a deployment. So service is not an encapsulation on top of a deployment. It is a different entity, but there's a mapping that if I want to create a service, let's say S1, I should say this service is targeting a particular deployment D1 so that the D1 gets access to the network so the customer can communicate with the code that lives inside the deployment as containers. Okay. So what we saw about monolith and microservices, that breakdown of monolithic architecture into microservices, this is exactly how we do it. So the reason we call it a service because it represents a microservice. Previously, we were only representing microservice as containers, but now we see that not just containers, a set of containers with replication capability and rollout capability, along with a service on top of it that lets it communicate to the network. Together, these features, we call it a microservice. Okay. Now, from now on, when you see, let's say, a large scale application, you know, broken down into smaller pieces, you can think of each of the piece is a microservice. Okay. And the microservice is basically a service attached to the deployment. A deployment is a replica set with rollout. A replica set is a pod with replication, and a pod is a collection of containers with some metadata, and the containers are packaged format of executable code. Okay. So with that, we'll just quickly move on to some examples where these sort of architectures are used. And one of the example architecture is the 5G end-to-end architecture. Um, this is not trivial, but this is the new standard and norm, I would say, that the telecommunication system since 5G, they have become cloud native. So there are new job roles for application developers who are software developers or software engineers to write softwares for telecommunication systems. So this is typically what a 5G infrastructure looks like. So your phone, for example, connects to a nearby base station, and this is done over an interface called UU or user interface. And these base stations, they create a network called a RAN or radio access network. And NG-RAN stands for the new generation of the RAN, which is the 5G radio access network. So all these towers that you see around you, they're all connected together and creating this network called NG-RAN. However, these towers, they communicate to themselves with a transport network behind the scene. So the way it works is each of these base stations, they are attached to something called a UPF or user plane function. And this is nothing but a router. And these routers, they create their own network using a transport network. So for example, you have fiber optic cables laid down beneath the surface of the earth, and this creates a very large infrastructure through which these UPFs are connected. So when you call somebody, let's say that person is not in the same RAN. So how does the call gets forwarded between nodes and the recipient, receives the call? This is where the transport network comes into the play. So this network mainly handles the traffic of the user, which is called the user plane, therefore the 5G CUP. And as you can see, the interfaces are standardized called N6, through which the UPF communicates with the transport network. And and on top of the user plane, there's also something called a control plane. And here we have various functionalities that are responsible for controlling how the underlying user plane should perform. For example, if you don't have, let's say, if your subscription has lapsed, you cannot access internet. So those kind of things that you can do on the 5G control plane. The example I just gave you is an example of a job of this policy, um, the PCF, policy control function, where you can define that, okay, I have gone through this subscription, so I should get that much of bandwidth. And if you are, so the network will try to give you that much of bandwidth based on the policy what is here. So these functions I will not get into. It's not relevant for this session, but they are all microservices. Okay, so now you can think of behind these boxes, there is a set of containers with some deployments, some services attached to it. And that's what the 5G architecture is. So therefore, we say 5G architecture is end-to-end cloud native architecture. Okay, so these microservices, they communicate to themselves. We have just seen that services are the component through which deployments can be exposed to communicate with other deployments. And this is called a service-based interface, or SBI, through which they communicate. Now, the type of interaction you do there, we just mentioned one of the interaction, which is the client server, but that's not the only way you can do it. So, for example, the 5G services based on the 3GPP specification, what standardizes 5G, there are two modes of communication which are defined. Number one is request and response. So, network functions cannot think of their like services. We can send a request, we get a response. Similarly to our the client and server we have for graph path calculation. This is one type of communication, but it's not the only type of communication. The other type of communication you can go for is subscribe notify. So in subscribe notify, what happens? You start with let's say a subscription. So you say, hey, I am subscribing to a particular event. If any time that event occurs, you notify me. So it's not proactive request every single time. This type of communication is called non-solicited communication. So you first initiate with a subscription and you expect that to keep getting notifications. A similar example of that would be when you join a WhatsApp group. So you don't need to go and check every time whether a new message appears there or not. Anytime a new message appears, you get a notification. Okay, and you can also add filtration, that which notification you would like to get notified with, and which notification you would like to filter. So those kind of things you can also do here. This second type of communication is called the pub sub communication. So publish, subscribe type of communication. So this is a different mode of communication, but both type of communication is possible between microservices. And some services I'd like to mention here, which are provided by 5G as standard. Number one is network slicing. So what you can say is I could have two pairs of devices connected to the same network, but let's say the red customer, uh, the pair of the nodes or pair of the user equipments or mobile phones that these customers are using, they might have paid less compared to the green customer. the green customer would get more resources from the network. So let's say more bandwidth, less latency, that sort of a service that the green customer might say. So this is what we call service differentiation. So we can differentiate customers based on what type of services to give them, based on what subscription they have gone for. And this is called network slicing. So basically, you're taking the network and logically slicing them, for example, with different resources based on the customer need. Now, there are specific way of giving resources, and this is defined by something called IMT 2020, which gives this diagram saying there are three major type of services, and these three services are the pillars of 5G communication systems, namely EMBB or enhanced mobile broadband, which is more bandwidth hungry services, which are more bandwidth hungry services. Massive machine type communication. This is where we see more IoT communication. So we don't need a lot of bandwidths, but we are dealing with a huge amount of devices. Think of a whole city might be covered with like thousands of CCTV cameras, and each camera would generate certain kind of feed, and this information needs to be somehow disseminated and assimilated by let's say a control and command and control center. So this is an example of massive machine type communication. And the third category is called URLLC, or ultra reliable and low latency communication. And this is where bandwidth or number of devices don't matter, the reliability matters. So, for example, when you make a change or some event happens, that event needs to be reported to somewhere within a given boundary of time. So they are very time sensitive applications. Industrial automation is one of them. You can think of that. If a industrial automation system, or let's say an assembly plant, if you face time drift or systems don't synchronize, then catastrophic event may happen. So therefore, there are three different types of main slices that is suggested by 3GPP, but you can actually mix and match them to create your own type of services. So you can't achieve all of them together. You can think of you're putting a dot in this triangle. So closer you are to a particular vertex, you will be inheriting the the capability of those type of services. So you can see some of the services are aligned here. So self-driving car is very close to the URLLC node. So obviously, because a car, for example, you bang on some object, the um, the airbags, yeah, the airbags must inflate within certain milliseconds. Otherwise, the only time you have to kind of hit the steering is less than half a second. So within that time, the system must sense a crash. It must start inflating the airbag, and it should inflate within that time by which you are supposed to hit the steering, and that also depends on your momentum and the speed at which you crashed. So this calculation has to take place at instant without any lag. So these are the sort of services where URLLC comes into play. Um, so whenever such thing happens, it should report to, for example, some command and control center that there is a car that crashed into something. So the medical service could get notified as soon as possible. So these are the example of different slicing, and these features are normally provided by technologies like Cloud RAN, which again, I don't want to get into. They're just cliffhangers for you. If you want to do more research, you can just go and read about them. There are plenty of videos available in YouTube on these topics. Go and have a look with this basic understanding of cloud native and microservices, how these ideas can be used to kind of understand how the modern telecommunication systems work. Um, Cloud RAN, and there's one more entity called MEC, or multi-access edge computing. These are the two prominent example of implementing cloud in telecommunication system. So you may have noticed that popular videos, they don't stream much. Sorry, they don't buffer much because because they're popular videos. So a lot of people consume it. So what happens? These videos are dumped somewhere nearby, the customer. Okay. So this place is called an edge server. So when you actually request the video, it doesn't go to the main server where the video is sourced from. So the access path becomes shortened because you only going to the edge server instead of going to the actual source of the video. So this is another example of cloud computing application. So as long as this video is most frequently viewed, it stays in the edge server. So all the trending videos you can think of, they stay in the edge server. So you don't have to use the internet resource to access every single video, trending video. Otherwise, you go to the main server to access it. As soon as that video does not remain trending anymore, that video gets removed. So this is the example of caching and algorithm like FIFO LRD you must have studied in your operating system courses. So this is how the concept of cloud computing is not just limited to application development, but the wider scope of cloud computing also encapsulates telecommunication systems. So telecommunication system is a new playground for software developers. You can use these tools and techniques you learn from cloud computing. You can also contribute that into telecommunication systems. So with that, that's the theory I wanted to cover. And today's session is more on hands-on. So I explained to you step by step how did I get to that point of just having containers into this Argo CD UI here. Okay, so let's start step by step. Before I move on, any questions? I can take 2 or 3 questions now. Okay, moving on to our hands-on. Let us first start with the build script. Okay, so the build script has these 2 commands. Let me just emphasize them a bit. So the build script, the purpose of this script is to build containers from the, sorry, not containers, the images from the Docker file, and then keep them in a local repository. Okay. Now see what I have done. What is the actual command that I have used? Previously, it was just a build command, but I've changed it for a reason, and you will see in a moment why. So the command is docker build x build, then platform Linux AMD 64, then -f, and the Docker file location, the actual file name, -t, the tag, and then the context. The context is the directory in which Docker file lives. Now, this bit was not there before. This minus platform and the build x, this part was not there before. Now, the reason we have it is when we build containers locally or natively, Docker assumes that the target environment is my computer where I'm building this. But as I also mentioned, that this is not the case all the time. You can build, for example, I'm building this application on Mac, and I might run in a Linux platform, and these 2 platforms are different. My Mac is a M4, so it's an ARM-based architecture. The CPU is a RISC CPU, whereas my VM is running in the Intel architecture, which is a CISC CPU. So obviously, if I build the image in my platform and I expect it to run on a remote platform, which is a different kind of a platform, it will not run. So therefore, Docker Hub, where we keep our artifacts, it kind of forces you to add the exact platform for which you are building the image before you push it. So even if you push it without the platform variable, it won't be pulled down until you set the platform variable. So that's why I have made this change that I'm specifically saying my target environment will be a Linux host. So, and the operating system is a 64-bit operating system, so AMD 64 architecture. This is my target environment. The reason we need this, because behind the scene, Docker will actually create the assembly for these platforms. So when you download it from Docker Hub, it can run natively without any issue. Okay, so the build tool I have changed from the last example. This is one. Um, and the next program I want to show you is the push.sh. So the push.sh is a basic shell script. It takes two arguments, branch name and the message that we use for the commit. Um, so basically what's happening, uh, if, for example, my number of arguments are not two, then this code will not run. It will give me an error saying that invalid arguments, and the usage is you call the push program and you pass the branch and the commit message as command and arguments. The first thing it does is, for example, I give a branch name, let's say test branch. It will switch to that branch. Okay, it has to switch to the branch because otherwise you stay in the main branch. You can also use switch minus C. It will create a new branch if the branch doesn't exist. But in our case, we assume that because we are kind of making any changes, we assume that first thing we do, we create the branch manually by ourselves. Then we add dot. So we track all the changes. We add a commit to that change, and then we push it, and we push it to a particular branch. So that's a set upstream flag. Okay. Now, with this, we can push the code in GitHub. But we also mentioned that this artifact stays in the Docker Hub. So the Docker Hub push is similar to Git push. Instead of Git, you are saying Docker here. So Docker push. And now I'm giving a particular signature. Now, this signature has three parts. The first part is this. Rishi Shiesi is my Docker Hub username, and I can show you that repository here. This is my Docker Hub username. If I go to repository, you will see some, some of these SPF client server that I built in the last couple of hours or days. This is a public repository, so you can pull it from. It should be somewhere. Okay, if I go to SPF client, you can see here that is the username, then the SPF client, and then the version. So first is the name of the user. So basically it's dockerhub.io slash the username. This is the repository where you'll find these images. Next part is the actual tag of the image. So the tag is SPF server, which is the name of the image, and the version. So just to be clear with this version nomenclature, we are using a type of version control called SymVer. So I think it's SymVer like this. Semantic versioning, SymVer, yeah, semantic versioning. So this is a specific way of managing versions. It has three components: major, minor, and patch. So x.y.z. Okay, so because we are still setting up um, this repo with um, just patches, so I'm not updating these zeros. It's just the last digit that I'm updating. Once the application is stable, then it is the first version, and you know how it works. Okay, so this is the build script. Sorry, the push script. I can show an example what happens when you push it. Let me do a bot solution, which is not recommended in production, but in desperate cases like this, we might sometimes do that. We go to the main branch and we make a change directly to the main branch without going through this push process, because that is somehow blocking me. The way you do it, you simply go open GitHub with your account and press dot in your keyboard. When you do this, you're going to open VS Code in the web, so you can do live changes. It asks you that do you want this to do with all these additional um, packages and extensions I have installed. I say yes, no issues with that. So I go here And what I can do now, I can directly go and make changes here. So see, replica was 1. Let me see if this works. So I change this to 5 and I save it, and I see that the Git has registered one change, and I give a message that update replica, and I press commit and push, and things looks like have gone okay. Um, how do I know that? I need to, let me move this, open my GitHub and that repo, Cloud Native. And if I now go to conf, I go to client, I see the replica has changed to 5. And if I now go to Argo CD and I make, let's say, a sync, you see just what happened. Automatically, the client side has scaled to 5 clients. This is what I wanted to show you since the beginning, that auto scaling, but somehow the push was not working. So I went through a very completely non-recommended way of doing things, is getting into the main branch and making things directly change there. However, we are doing a test here, so we are okay to do things in experiments like that. Okay, so I think the goal is now set. Okay, we are going to design this system and we need to understand or demystify what's going on here. What are these namespaces and other things here? So the next half an hour will be very, very involving. So I want full attention from all of you. Um, right. So we are going to understand this image, what it says, this image. And this image I have already updated in our draw.io file that I have shared before. So it should be somewhere, let's see. Um, and I will change the appearance to light. That will make it more visible. This. Okay. What you are seeing here is what is called the pipeline of a DevOps process. Okay. I'll copy this and I'll paste it in my PowerPoint so we can have a better view. Now, all right. Okay. So what are we going to do here to understand this different components and how they're connected? So an operative is a person who would manage a cluster. The operative manages the cluster through a tool called kubectl or kube control that remotely connects to a master cluster. A master cluster is the control plane of a Kubernetes cluster. And this is done by RESTful calls from the kubectl and the master. Now, how does the kubectl know that where the master is? Because the kubectl can run remotely even. So it does it through a particular file called kubeconfig file. And a kubeconfig file uh, contains all the necessary information. For example, the IP address and the port number at which the master is hosted, plus some security keys through which this master can be accessed with defined privileges. And the master then has control over a set of worker nodes where the execution actually takes place. It is the worker node in which we run a set of services, hence we call it microservices. Here you can see there are 4 such services. One is Argo operator that will come to in a moment, but please understand Argo as an operator runs as a service inside the cluster. Then we have this client server peer. Okay, so these are the 2 services of the same application. Therefore, I use the same color. There could be a custom networking between these two services. So the service based interfaces we just saw in the 5G architecture, this is the same idea. This is facilitated by something called service mesh, which is beyond the scope of our discussion, but you can have a look what service meshes are and how they work. So basically, they provide virtual networking between the services. And there could be other services, which are these three dots that represent any other services in that cluster. Okay, so in our case, the customer would communicate with the client side of the application. So the idea is the server will always stay hidden from the customer. The customer should not know where the server is. That would be a security flaw. The customer would communicate with the client, and the client will make all the necessary calls to the server. Okay, so the client will become the front end through which the customer communicate with the applications. I believe we already had a session on back end and front end, so you know this architecture. Now, from this, what I also mentioned that whether that application that we are deploying here, let's say SVC client and server, they are running as we desire or not. This is something Kubernetes cannot automatically synchronize. For example, if I say that my application would require a certain amount of memory and CPU, and if while running the application, the memory and CPU are not available in the system, in that case, what happens? Kubernetes may fail running the application, but that is something the developer might not know. So it has to kind of ensure that somehow this desired state of the system gets synchronized with the runtime state of the system. And this synchronization is called reconciliation. So in reconciliation, we reconcile between the desired state and the runtime state. So how do I mention what a desired state is? We'll see that in a moment in the code. So just think of that the pipeline goes like this. The developer who starts the process, he builds or run the application. I actually forgot to change it. Developer, it should be developer, not operative. It's a typo. So the developer writes the code and it goes through a process called the CI pipeline or continuous integration pipeline. And it has three phases: build, test, and package. Build, we have already seen. Test, we don't need for this, but in a real system, you need a test that tests the application to its edge cases, that whether the application fails in some cases or not. You know, the boundary value analysis and equivalence class partitioning techniques that we study in software engineering, that goes there. And then we have packaging, where we package the application in containers. So these are the build and package steps that we just saw in our build script. Once the build is done, then we make two push. One push is towards Docker Hub, where the build artifacts will get stored, and the other push is the GitHub, where the source code gets stored. Now, this source code also contains what is called the desired state. This will be an extra folder in your source code, normally called conf or config. And in this folder, we'll keep some files written in a particular language called YAML. YAML stands for YAML ain't a markup language. It's a recursive definition. So YAML is not a markup language. As it says, it's a language which is used for data serialization, just like JSON or XML. But YAML is found to be more interpretable by human. Okay, we'll see some example of the YAML files. And these YAML files would contain different kind of information. The the core philosophy of having these files is to encapsulate something called infrastructure as code. So we will write a code that will define an infrastructure in which we expect our application to run. So basically what happens that this desired state will have an internal link with the images that these YAML files will use while spinning up um, pods and execution environments. We'll see how to link those as well. These will be pulled by the Argo operator. So Argo is this reconciliation operator, and it will communicate with the master node. So basically what happens, the master node knows where to fetch my images. There will be Docker Hub, and it also knows where the desired state of the images are. That will be in the GitHub. Now we pull those desired state from there, and this operator also keeps polling the GitHub repo to see. So the idea is this, that the Argo operator will keep on polling to go for changes or look for changes, that if there's something has drifted from the previous state or not. If yes, they're going to pull down the current version of the state, and then it reconcile it with the master that, okay, so the state you're operating now is outdated. The present state is this. The example you just saw, I changed my replica to 125. That's a drift. So my initial state was one replica of the client, but my desired state now has changed or drifted to 5 replica. So when we do that, we expect the reconciliation tool to kind of do this synchronization automatically. So no matter how the existing state is, it will try to take your application state to the desired state. This is a very common practice in what is called a desired state system. So not only you write the code as a developer, but you also define what execution environment you need to run the code. Okay, because the last thing you want is you end up having some fatal error, for example, in out of memory or out of resources issues that kind of stops your application to run, not due to the a flaw in your application, but a flaw in the system you're running the application. Okay, so you need to be very clear about the reason why we need reconciliation in the first place. And then when everything is running, then the customer should get access to the client side. And this is what the idea of services is. And we sort of do this communication over the network. So all these connections between the boxes, so the op box, the cluster box, the repo and registry box, the developer box, and the customer box, all these boxes, they are geographically distributed in general. Okay, so the operator may run in a different, may work in a different country perhaps than the cluster. The developer can run in a different country perhaps. So all these links are over the internet. So this is a very simplified diagram instead of putting internet everywhere. um, and that's why I have color coded them different so you can understand how the communication takes place. But all you need, an IP address and a port number. The role of internet is to route your traffic to the IP address of your interest and the port number through which the service is getting served. So let's see in the code how exactly these things are done. All right. The first thing I'll show you is the desired state, and the desired state in our case are kept in 2 files. The first file is the SPF client.yaml and the SPF server.yaml. These two are the 2 files in which we kept information in a format called YAML format. And this is how a YAML file looks like. Even if you don't know this language, even if you have no clue about how to write infrastructure as code, given the information, what you just heard, if you just read this file, you will get some information. You see what I'm saying here? So in YAML file, first of all, we have certain segments. So this is one segment, this is another segment, and they're separated by these 3 dashes. This is a YAML notation. So instead of having 3 YAML files, you can put all the info in one YAML file by separating them in this way. YAML file is always read from top down, just like GitHub, just like Docker files. So what I'm saying here is I am starting with an API version v1, which has a definition of a namespace. A namespace is an execution environment which is isolated from other environments. Just like container runs a code in isolation, and if you can combine containers, you create a pod, you add certain layers of functionality on top of it, you get a deployment. Now, if you have multiple deployments, then you can put them into another kind of abstraction called namespaces. So if you remove that namespace, means you remove all the deployments within it, means all the containers within that deployments. So it's just one piece of execution environment. If you want to just uninstall everything inside it, remove the namespace. That is the use of namespace. So you don't mix and match with other running applications. The core idea is every application should run with its own namespace. That's it. The application that we are running, we are calling it SPF. Sorry, the namespace in which we are running the application is SPF app namespace. Now, this namespace is same as if I go to the server file. So you see the client and server has the exact same namespace defined. So that tells you what? When you run these applications, both client and server will reside in the same namespace. Yep. What are we putting in that namespace? How do I define a client now? Previously, my client was basically a container, okay, a Docker file initially, and we create an image, and now we pushed it into a Docker Hub. So that was my um, module, or uh, the the microservice that we were treating before. Now with this, what we have said, these microservices are now encapsulated. We are using the encapsulation called deployment, and deployment is defined in the API version apps v1. Please pay attention to the verbs I'm using. I'm saying that the API version is something where these kinds are defined. So all these example I'm giving, namespaces and deployments, they are coming from particular versions of Kubernetes definitions. So you must be very specific to which API version you are using, because otherwise this deployment will not get, Kubernetes will not find definition of that sort of kind that you are um, referring to. And this is not a difficult thing to do. You can simply go and search for Kubernetes deployment. Let's say you'll see examples, and there you can find which version of API is used to define that particular resource. So namespace is a resource defined in API version v1. Deployment is a resource defined in API version app v1. I give a name to this deployment called the SPF client dep. Dep stands for deployment. And I say this deployment will run in a namespace called SPF app NS, which I already have defined. So again, YAML files are read top down. So if you don't create the namespace in the first place, you won't be able to assign a deployment to a namespace. So having a namespace is a prerequisite before you assign a deployment to a namespace. Then we go to the spec, which is a specification of this particular deployment. I say that I want 6 replicas of the deployment. Um, and this is something that coming from the replication controller. There's something called selector and match level. So basically what I'm saying that this particular SPF client is going to be my label, okay, where this label will be used. So if I go now to my services, I said that services are not encapsulation. They are a different entity, but they maintain some kind of mapping. So if I say I am a service, my name is SPF client service, and I want to map myself with SPF client deployment, how would I do that? I say in my service that, you know what, you go to the specification, go to a selector and select the label, which is app SPF client, the same app SPF client, which is labeled in my deployment. So can think of this a logical link through which I kind of refer which deployment to connect with which services. So you can play with it. There are 2 different definitions, and in this way, this part of the file can stay in a complete different YAML file, yet they can relate to themselves by means of these labels and selectors. So for more information, you may have a look on what Kubernetes labels and selectors are and how they work. So this will be helpful to understand how not only service and deployments, but in other Kubernetes resources, how they're linked. A very important part is a type of service. So Kubernetes supports three types of services, namely node port, cluster IP, and load balancer. Node port is similar to what we saw last time, that you reserve a port from the physical host. Although this is the simplest solution, but you can guess the issues with this approach. Just think of, there are two physical nodes in which you are running your cluster, and these two physical nodes have different ports exposed. A service perhaps were running in one of these two nodes. For some reason, the service died in that node, and when the scheduler of the Kubernetes control plane rescheduled it, it scheduled it in the other nodes compared to where it was running before. Now, if the service was configured as node port service, it will try to allocate the port from the new node, right? But what if that particular port is already reserved by some other services? Then this service, despite of just getting rescheduled into a new server without any flaw, it cannot run because it will get a port conflict. So as a developer or as an operative, you cannot be sure about the fact that every time you move an application from point A to point B, you will have the ports available for that application. So that issue is always there, and therefore we need some sort of flexibility in this case, and this is where load balancer IP comes in. The other example is cluster IP, which is making a logical IP address which is only accessible or locally significant to the cluster. But most of the cases, your application will be accessed from external devices. So therefore, cluster IP is good for debugging and troubleshooting, but it's not very useful when you um, access application from external sources. So mainly, the rule of thumb is typically for services like this, you go for load balancer services. Now, I don't want to get into details about load balancer. It's a different concept. There are some theory which are required to understand how exactly load balancer works. I leave it to your own research after the session. Um, so basically, load balancer, the way it works is I'm saying that my communication will take place over the protocol protocol TCP, and I'm gonna just create a new service named HTTP, and this HTTP service will listen to port number 9001 externally, targeting 9001 internally. So that port mapping that we did in Docker -p flag, that is similar to this. Now, obviously, you can understand from this description, because YAML is more humanly comprehensive. Therefore, it tells you exactly what it is, port and target port. So you can go and have a look in your in the Kubernetes manuals what exactly they mean, instead of just putting a -p flag that we saw in Docker. So I would say this idea of infrastructure as a code is more user friendly compared to what we had before. Now with that, we can move to the server, and the description is almost the same. We create a namespace called SPF app NS. Now the good part of Kubernetes configuration is they're idempotent in nature. Means if you run a command already and you rerun the command, and both the command does the same thing, the second command is ignored. So you only execute a command if you see the command will make some changes to your system. So if we run client or server, anyone before the other one, so the first one will create the namespace. The second one will go and check that whether the namespace exists or not. It will see that namespace already exists, so we're gonna skip it. Then it goes into the deployment definition. We have the SPF server deployment running in the SPF app namespace with one replica. We give a label called SPF server, and this label will be referred in the services. So far, I have discussed how the Kubernetes service and deployment looks like, but I haven't talked about how does this deployment know where from I should pull the image. So this example, how does the deployment know that where the Docker Hub image is? and this is where you define it. So inside the deployment specification, if you go to template and you go to specs inside the template, you will find containers. And in containers, you will find image. So this is exactly where my image or my Docker artifact, Docker image or the artifact is placed. So if you recall, this is the exact same location where I showed you my Docker Hub somewhere here, and this is the exact same location, Rishi CC24 SPF client, then colon, the tag is v001, and for the server is the same with SPF server. So if I make a Docker tool from this particular tag, I should pull the image, and that is something which is defined in, not here, in my image key value pair. Okay. There's another example here is called pull policy, image pull policy always. This is mainly useful, for example, if you already have the image in your local registry. If you don't have it, then Kubernetes might skip downloading the image if it finds the image name is exactly same. So it relies on the versioning, that if the image has changed somehow, so you must change the version, which should have been the case. I am not doing it because it is just a demo. But if you have this pull policy set to always, means every time you run this YAML file, it will go and fetch the image and replace the existing image, regardless if you have it or not. And then we say that container port is 9000, because this is exactly the port what we exposed in our Docker file. If you remember, in the app, we had a Docker file, and a Docker file had this port exposure. So 9001 is for the client. So if I go to the client's YAML file, we'll also see 9000. Okay. And finally, this is a static IP, which is my host computer's IP address. This is the IP through which I am connected with. And things looks all good. Okay. So I'm moving on with the cluster creation. So Kubernetes clusters can be created in different ways. One which is recommended called the installation through kubeadmin. Um, this is the longest among all the different alternatives you have to install Kubernetes, which is normally using in production, where you have full control or autonomy, that what exact features you want from Kubernetes. You can make some changes in installation. But in our case, in fact, just installing Kubernetes through kubeadm would be a course by itself. So normally for developers who would just try to spin up a cluster locally and test things, people don't do that. There are other ways of doing things. One of the possible way is called um, uh, using a feature called kind, KIND, and kind stands for Kubernetes in Docker. So Kubernetes, we know, is a cluster computing operating system. So it relies on clusters. Um, you can actually create Docker containers to make that infrastructure for you. So what you can do, you can define the entire Kubernetes cluster configuration in a file. This file is the k3d config.yaml file. It is also a YAML file, so you can see that it's written in a YAML format, but it is not the same Kubernetes manifest that we saw. So the format is same. It has some different descriptions. So what it says that I'm going to create a cluster. I will call it SPF cluster. And this cluster will have one master node and two agents. This is exactly what we had in this setup, one master and two agents. And we're going to put certain configuration that this will be hosted in this particular IP address, some port number, which is default for Kubernetes. I will expose and port forward this 9000 and 9001 port. This will be eventually used by client and the server. And then I've got some other information which are not required for discussion at the moment. You have access to the repo. Base thing what you can do, you can copy this YAML file, give it to any generative AI tool to explain it. You will get more explanation. That's how you need to kind of skill up yourself from now on. You don't need to go to manual for every time. You can simply use generative AIs for clarification. Okay. Now, once this is done, we can now come back to our GitHub repo and go through step by step how to create a cluster from scratch and how to um, sort of onboard application into it. So if I go to my README now, we have added this figure. I just explained this figure and different, the whole pipeline starting from the operation side, developer, and customer. So operation side we have already discussed before, um, or we will also take a look in a moment about the kubectl tool. Developer side we have discussed in the last lab. Docker Hub we have seen, GitHub we have seen, customer we have seen. Now the main part, which is this cluster, which we are talking about since the beginning, but we haven't actually described what it is. So to create a cluster, you first need that Kubernetes, the K3D config file. For that, you need to have the K3D tool installed that will create the cluster for you. So run these 3 lines of code that will download the K3D tool from the internet, and then you can run this command called K3D cluster create, and then you provide the config of the K3D config.yaml. Due to shortage of time, I'm not stopping my cluster and doing it from scratch, but I leave it to you for your own practice. If you just copy this install.sh file from K3D's official source, and you have the K3D config.yaml file with you, and you run this command, this will create the cluster in the backend. Now, the kubectl tool that I described, it is a CLI tool through which you communicate with the master. And this is a tool which is available in Snap. It is a Ubuntu package manager which you can use to install kubectl. So this is not kudo, should be sudo. I'll change it. Sudo snap install kubectl. Classic will install kubectl for you. And once you are installed with kubectl, this is something you can do with it. So let me actually go to the server. So let me SSH to user at the rate 10.120.59.70, and I give my password. And then if I say kubectl get nodes, so this will tell me how many nodes do I have in my cluster. And as you can see, there's one server and 2 agents. So these agents are the 2 workers, and this is a server. So you can say role is assigned as control plane or master. Okay. Once done, then so it also tells you how to revert. So if you already have a clustering like me, so you can go and paste this 2 line. It will remove kubectl from your system and gonna delete the cluster that you have. Next is an optional process. So what if I want to onboard the application without using Argo CD? So in that case, I could use this SPF server.yaml and SPF clients.yaml, and I can say kubectl apply this YAML. Okay, so apply -f tells us that I want to apply a YAML file which has the infrastructure as code. And what this command does, it basically applies the file in the Kubernetes cluster. So you create the deployment and the service and do every single thing that you have mentioned in that in those YAML files. However, this is not what we want to do, because if you do it the deployment in this way, and if tomorrow the deployment fails for some reason, you need human effort, manual human effort, to go and stop the deployment, debug issues, restart the deployment, which is again not an automated practice that we want to achieve in a cloud native system. This is something which we are going to achieve with Argo CD. So Argo CD, the process is a bit lengthy process. I'll go step by step to explain what is happening. So if you can do it from your side, you just follow the steps. The first thing we want to do is to add this Argo CD capability to the existing Kubernetes orchestrator. Means adding reconciliation as an extra feature on top of the vanilla feature set that we get with K3D version of Kubernetes. Just a quick reference point on that. So K3D is referred to as a Kubernetes wrapper, which uses um, another system called K3S, and K3S uses kind to deploy itself through Docker. If this doesn't make any sense, that's fine. You have the recording, and I'm sure if you rewind it back after the session, and if you take this and do your own research, it will make sense. Okay, but in your mind, that's how you map it. What K3D is, what K3S is, what kind is, and how Docker is in the scene. Okay. Um, so the first thing we do is we create a namespace. So kubectl create namespace will create a namespace called Argo CD. A namespace, as I mentioned, is a place where you put various Kubernetes resources, and then you run this command: kubectl apply -n, which is defining the namespace Argo CD. Then certain other things, server side, and then force conflicts as flags. And previously, what we were doing, we had these files locally. We would say apply -f and the file name. Here we are saying apply -f, but not a file name, but an online manifest. So this file is hosted online. You can just copy this and you can paste it, and you could see YAML basically. So you see that this is nothing but a YAML file. The only issue here is this file is not locally placed because Argo CD people, they keep updating this file. So whenever you call this function, you always get the updated version of the script. This will add Argo CD to your cluster. Let me quickly show you how does it look like. So from the cluster point of view, if I say kubectl get namespace or ns, I should see all the namespaces we have. And here we have Argo CD somewhere, this. I can also say kubectl get all -n Argo CD, which means that I want to see everything that we have inside the namespace, and you'll see a list of resources. These list of resources are something that I haven't created. What happened when I called this command? It went to this file or this URL, it dumped that file locally, executed it, and created that whole resource for me. For the very first time when you run Argo CD, it will require a password from you, which you can fetch from this command. So if you copy paste this command, you will get the default password which Argo CD generates when it starts. And then when you go to Argo CD UI, you could log in with that password. Before that, you may also want to expose Argo CD over the network so you can access it um, from remote computers. Copy and paste this command, and what this will do, it will make a port forwarding, and it will forward the 443, which is the HTTPS port, to a port 8080 through which you can access it. And just like the previous example we saw with UVCon, it will not discriminate between any address from which the request comes. So therefore, when I go to Argo CD, you can see the port number here is 8080. I can just close and restart, and we can see that we can access the application. Okay, so now Argo CD is being hosted. We have the namespace created. The operator is added on top of Kubernetes. The next thing we need to do is the configuration. And this is the most important part of the session, because if you think of the diagram that we show in the previous, this diagram, you can think of the Argo CD is the only operator that links both the cluster and the repository. So it has one pointer that is polling the GitHub repo for looking for changes, and the change happens, the drift is detected, and you get that repository pulled in, and then you reconcile with the master controller. So you need to have both the pointers, one towards the cluster, one towards the registry. Where do you set that? Go to the application. I've already created one, so I can show you from this only. Or you can also create a new application to see those options, but this is how you see it. So test application is an Argo CD application which is reconciling. I go to details and I get a form filled up with a lot of information. The first information I see is a cluster. And the cluster is the local Kubernetes cluster because if you remember, I'm running Argo CD on top of my current cluster. So it will natively find what is the local cluster I'm running with. That's this pointer, the pointer towards the master cluster. The other pointer, which is this repo URL, that goes to my Rishi CSE 24 cloud native demo.git, which is this, my GitHub repository. Okay. Now, my configuration, which I call the desired state, are not directly in the root folder of my my repository. It's inside the conf folder. So I have to specify that it's not just a registry, but which subfolder Argo CD should watch for the desired states. And this is what I can do with the path variable. So the path variable says that inside the repository, there will be a folder called conf, and you go to conf and you will find exactly what you're looking for. So if I make any change in that conf folder, it should automatically trigger Argo CD that you know um, reconcile. Okay. So this auto sync and prune resources and self healing, all these features needs to be turned on to make this reconciliation smooth. And once everything is done, you will be welcomed with a display like this. Now, I believe this would be much more comprehensive to understand. I have a Argo CD application which is bridging or reconciling between my GitHub repo and the cluster. The application has a namespace defined called SPF app, inside which I'm running two deployments, namely SPF client, two deployments, SPF client deployment and SPF client, SPF server deployment. And these two deployments are linked with two services, SPF client service and SPF server service, respectively. So the client service is exposing my client application, which is SPF client deployment, and the server service is exposing my server application, which is the SPF server deployment. These deployments are then get interfaced with a replica set. This RS stands for the replica set. So if you remember, deployment is the outer layer. The inner layer to that is a replica set, and the inner layer to the replica set are the pods. So how many pods are we creating here? This is defined in the replica. So if I go to my client, I could see that the replica is set to 5. And therefore, I've got 5 clients running and 1 server running. So if you recall something I defined or discussed in the last class, that the whole point of cloud native is to allow heterogeneous scaling. Means we could say that a part of the application may scale differently than the other. This is an example. So the client has scaled 5 times compared to the server side. Okay, this could be the other way around. I can go to the same repo. I can go to the server side and I can change the replica to 10, for example. And whenever I do that, I see a modification takes place here. I go to my Git source control and I say comment here. Let's say update server replica, and I don't normally use spaces in my commit messages. So that's it. I push that change. It will directly make a change in my main branch. So if I now go and check it, it should be 10. And now if I go to my Argo CD, you see automatically, I didn't even touch, automatically the number of application has scaled to 10. Okay. I will stop my demo here because this is what I wanted to show. I just want to add one extra thing which I didn't cover in the demo, but it is normally covered in or followed in best practices. If I go back to this diagram, if you see how Argo CD communicates with my GitHub repo, it is a periodic polling mechanism. Okay. Now, by default, Argo CD's polling interval is 120 seconds. So not actually 120, 150 seconds. There are two entities there. One is the polling interval, which is 120 seconds, plus I think 30 seconds for something called a jitter. And it adds these two, and for every 150 seconds, you're gonna make a poll. But what if, so this idea is more of like initiated from the Argo CD. You can lower it down to 5 seconds, what I have done in my case, and the configuration is something you can also find in the optimization section of my documentation. Here, reconciliation optimization has described this 3 minutes or 120 second plus 30 second, 150 seconds of this periodic check. But you can also change it with this command. And here you can see the reconciliation time is 30 seconds and jitter is 0 second. You can change it to 5 seconds, 3 seconds, whatever you want. And then if you just run these two commands to roll out Argo CD because you have made a configuration change, and you should be able to see the change in effect. Just follow this part of the tutorial. So this is not a good way of deploying automation because if you keep this timer too low, like 1 second, for example, it's gonna be massive to your network because every single second for every single app, Argo CD will make a poll request. That is a huge network overhead. And it is not very frequent that you see every single second you see changes in a repo. So the better approach wouldn't that be if we could somehow set up some mechanism in my GitHub that anytime we have a push or anytime we have a PR accepted changes, the request instead of getting initiated from the Argo CD operator, it get initiated from the GitHub repo itself. This is a concept of a webhook. So this is something I'm leaving for you guys to do your own research. So in a real environment, after all these things, the next thing what you would do, you don't change the polling timer of Argo CD. Instead, you will set up a webhook between the application and the Argo CD. So anytime there's a PR getting accepted in your GitHub repo, that should initiate the reconciliation process. So instead of me doing all this synchronization manually, because I've set my timer very low to like 3 or 4 seconds, that's why you could see that change just took place right after I did it. But had my timer be sometimes something like 120 seconds, this wouldn't have been the case. Okay, so that is all I wanted to show. This is the full deployment of a source code first getting containerized with Docker and then deployed in a Kubernetes cluster starting from scratch and then applying reconciliation between the cluster and the repository. So that's my time. I hope this was informative for you. And if you have any questions, you may start firing. I would like to reserve 5 more minutes for if you have any discussions to make in terms of your career choices. Yeah, it's 5-10 more minutes I can spend now. Thank you.
So, good morning, good evening, sir. My question was like in a hypothetical way, if we suppose we don't use Argo CD, so and we use directly cluster to GitHub away, found a way that do it. So, what problems would it create? And you mentioned that webhooks, like we use
Mhm.
webhooks, so we don't poll. So I have used webhooks, and I've seen that many applications have their many websites have their own created webhooks, so we can use it. So is
Mhm.
there a way, is there any application that exists now that creates a bridge between GitHub and clusters?
So the tool that does this bridging is called the reconciliation. So this is the class of the tools called reconciliation tools. Okay. There are three of them which are available in the market. One is called Config Sync, which is from Google. Argo CD, just saw it. And the other one is Flask CD. So Flask CD, Argo CD, and Config Sync are the three tools. Just in case if you are interested, so this paper, um, yeah, I can't access it now because I haven't logged in. But this paper actually talks about the performance evaluation of the three most popular GitOps tools. So we have used scaling the application, scaling the replica of the application, different types of benchmarking we did, and you could get more insight there if you wish. So the tool itself is called reconciliation tool. There are these three different versions which are available, and webhook is an add-on on top of reconciliation. Reconciliation by default is a polling-based mechanism. If you want to make it event-based, you need to use a webhook. I hope that answered your question.
Yeah, thank you, sir. Sir, I was asking that all that diagrams and are these publicly available? We can like.
Oh yeah, yeah. So I believe I shared this repo link with you guys already. So I made some updates yesterday on the repo. So you could whatever I just covered today, because I knew that I couldn't do it like live. So I put all these things as instructions in the GitHub. So it's a public repo, Rishi CAC 24/cloud native demo. Uh, go for it, and you'll find the full all the diagrams and the step by step guide. So the thing that we covered last week, sorry, yeah, last week, is in the first part, Docker installation, and then we have got an extra bit here, which is the push script I discussed in the very first part of this session today. And there are three tasks, which is deployment of Kubernetes, onboarding the applications with Kubernetes manifest, and then integration of Argo CD and its optimization.
Yeah, thank you, sir.